my screen, when it's increasing, that means above the x-axis. So where is it above the x-axis? It's here. It's here. Okay. And then it's decreasing. I'm going to switch colors here. When it's below the x-axis. So in here, this window, and that's it. So now we actually got to give the like the intervals of that.
Mhm.
So let me do the below. So we assume this goes forever. So it's minus infinity to -2, comma 0, comma 2, comma 2, comma 4. I've excluded 2 because it's touching there at that point.
Mhm.
So it's not really there. And then above is the -2 to 0, comma 4 to infinity, because that's we assume that goes out forever.
Right.
All right, so a local max occurs, and the nice thing about this format is I can actually grab that image again here and snip it in here. So the max occurs, you get a max when the derivative goes from plus to minus. And we know it's positive when it's above the x-axis. So basically when it goes from above to below. So that occurs here. And that's it. A min is when it goes from minus to plus, below to above. There's actually quite a few more of those. So that's a max. Here's a min because it goes from below to above. These are just definitions. Nothing there because it actually doesn't change. But here it is a min because it goes from below to above.
So it wouldn't be 5, wouldn't be the max. Like
No, because we're looking at the derivative. Everything we're talking about here is because we're looking at the graph of the derivative.
Mhm.
That's why the rules are unclear, I suppose.
Okay.
If we're looking at the original function, absolutely, it's got a max there. It's max,
Okay.
min, local max, local min, local max. But we're not. We're looking at the derivative.
Okay.
Everything changes. And that's why I try to give you these like guidelines here to remember.
Right.
This is, rules, but they're helpful.
All right.
I can't recall. Do we need to do some curve sketching? C is to sketch the graph of the second derivative, and then scratch the graph of the original.
Yeah, we'll just do it.
Okay.
Just to be safe.
Of course. All right. So now the derivative is actually easier to graph than the original. So what I like to graph it right below it. Some people graph it right on it. But the first thing I look for are these peaks.
Mm-hmm.
These are all horizontal tangents. And these are all zeros on the derivative graph, which in this case is the second derivative. So down here is the second derivative graph. Okay, so now, do you see how the graph is going up? Here it's increasing.
Yep.
That means it's positive here, but it's got to connect at that point. Do you see how the graph of this one up here is decreasing?
Yes.
So that means it's below the x-axis here, but it's got to connect back to that point. Here it's increasing because it's going up. So that's why it comes back like this. Here it's decreasing from 2 to 3. Did I miss one? I did. I'm so sorry. I missed one of these. There's another one. So it's here, and then from 2 to 3 it's decreasing, so it's like that. From 3 to 5 it's increasing, so it's maybe a little bigger. And then here it's decreasing forever.
All right.
Actually, I take that back. Because the slope comes back to 0, it looks something like that. That's kind of the easier one because it's like going in the forward direction. The graph of the original, you have to like figure out how to go backwards.
Mhm.
It's a little bit tougher. So it's like doing everything we just did, but in reverse.
All right.
So wherever the derivative is 0 means that the original function had a min or a max there. And that's why I'd asked like min or max.
Yeah.
Okay, so at here it's a min because it's going from negative to positive.
Mhm.
So it's some sort of like min.
Okay.
This is some sort of max here because it goes from there to there. We already did this. I'll just,
Yeah, you don't have to make it pretty.
right. And then this right here is yet another min. I'm sorry, this is nothing. This is just a horizontal tangent. So it actually comes down. Okay. And then here it's another min. So it like mins out right there. And then something like that, up like that. Really rough. But that is approximately what it could look like.
All right. I want to do the 9 through 14 ones.
Okay.
I'm thinking the most, honestly, all of them but 12, I think, could be on the test.
Okay. That's a long test.
Yeah, it's 2 hours. So
You're over preparing, which is probably good. So horizontal.
they could be, not all of them, like, but those are, do you know what I mean? Not every single one.
Well, what I believe is you're going to get A through E, but like A and B don't apply to this question because there is no vertical or horizontal asymptotes.
Okay.
I'm sorry, A doesn't apply. So this is NA for this one.
All right.
For B, to find the intervals of increase or decrease, you got to take the derivative.
All right.
Your derivative here, your f prime of x is it's -2 minus 3x squared, and you set that equal to 0, and you solve for x. So it ends up being 2 equals 3x squared, 2/3 equals x squared, x equals plus or minus the square root of 2/3, plus or minus the square root of 2 over the square root of 3, and then you have to rationalize here. So you get plus or minus the square root of 6 over 3. So on your number line here, here's minus square root 6 over 3. Here's positive square root 6 over 3. And we got to test points to see what's going on in each interval. Do you recall doing this?
Yes.
Okay, so when we test like 0, it's 2 minus 3 times 0 squared, which is 2, but it's a positive number.
Mhm.
And you want to choose something like way over here, like 10. That way you're not even close to this. So 2 minus 3 times 10 squared is definitely a negative number. It's like 2 minus 300. Negative 10, it's the same deal. Negative 10 squared is 100. 300, 2 minus 300, you get another negative number here. So this tells you where it's increasing or decreasing. It's decreasing from minus infinity to minus square root 6 over 3, comma, square root 6 over 3, comma, infinity. It's increasing from minus square root 6 over 3, comma, square root 6 over 3.
And then the concavity or concave up or down. You just take the derivative of you take the second derivative. Right.
Say that one more time. I'm sorry, I didn't get it. Was
To find concavity, what's it called?
yeah, concave up. Yes.
Right. You
But
take
we're
second derivative.
yeah, but we're still on C because like one of these is a min, one of these is a max. So the min, because it goes from minus to plus, that's a min. And because it goes from plus to minus, that's a max. Okay, so now concavity. So like you're right. So now part D, the second derivative is minus 6x. You set that equal to 0. And you find that x equals 0. So now you do a sign chart for the second derivative. And you test points on the left and test points on the right. So when x is positive, it's negative 6 times a positive number. So that's negative number, you get a positive here. So it's an inflection point when you go from plus to minus or minus to plus, but you have to be looking at the second derivative.
Right.
So now it's concave up from minus infinity to 0 and concave down from 0 to infinity.
All right.
Okay, so I think that takes care of A through everything on that.
Yeah, I don't think we got to do. Yeah, let's do. Can we do 10 next?
Sure. Give me just 30 seconds here to take a short, just need a mental refresher here. Give me a moment. All right, so you said question 10. We should definitely do one that's got a horizontal vertical asymptote, and this one finally has it. So 10 is a good one to do. Unless it's got different derivative than the others. Okay. This one has a vertical asymptote when 1 minus x squared equals 0. Because you set the bottom equal to 0. You got to be careful here because you got to make sure you recognize there's two solutions. It's plus or minus 1. So there's actually two vertical asymptotes, two VAs. It does have a horizontal asymptote. Do you recall this from your previous math classes that you look at the degree of the numerator and the degree of the denominator? Okay, so because the degree of the numerator, which is 0, is less than the degree of the denominator, which is 2. Okay, it always has a horizontal asymptote y equals 0.
Okay. And when they're equal, you just take the ratio.
Yes, the leading coefficients. Okay, so now we're on to intervals of increase and decrease. We're on to part B.
If the numerator is bigger than the denominator, then it doesn't exist, right?
That's right. It's a slant asymptote.
Right.
Ends up going to infinities most of the time, plus or minus. All right. So now you got to take a derivative of this. Now you might recognize how to do the derivative if I rewrite it slightly. Like this. It's power rule followed by chain rule. this -1 means the 1 over. So it's -1 times 1 minus x squared to the -2 power, multiplied by the derivative of the inside function, minus 2x. Is that okay?
Yep.
All right, so we do want to clean this up a little bit. This negative and this negative go together. It's 2x over 1 minus x squared squared. So we set this equal to 0. And you actually only need to set the numerator equal to 0. So it's 2x equal to 0, x equals 0. So you make your sign chart here. Okay, and this is the derivative, okay? And you have a place at 0, but you told me that there's vertical asymptotes at -2 and 2. And while those aren't critical points, this is the only one that's a critical point. You can't test, you have to test on both sides of this.
There's -1, 1, right? It's the vertical asymptotes.
Yes, thank you. Thank you. -1, 1, yeah. So we test numbers. Now notice the denominator is always positive, because when you square something, it's always positive. So it's just the sign of the numerator. So in this case, you might not have seen it, but it like if you try 1/2, it's positive. If you try 10,000, it's positive. And this negative, but it's important to differentiate between them. So now the increase and decrease, decrease here, you got to be really careful. It's -infinity to -1, comma, -1 to 0. And the increase, 0 to 1, comma, 1 to infinity, because they're not part of the domain. All right, now there's only a min or a max based on the changes in the sign, but it's only where the critical points are. You can't look at these breakpoints. So since it goes from minus to plus, this is considered a min.
All right.
Is that okay?
Mm-hmm.
All right, now we got to do the second derivative, which is horrible. Okay, so our first derivative is 2x over 1 minus x squared squared. So your second derivative is the bottom function, 1 minus x squared squared times the derivative of the top, 2 minus the top times the derivative of the bottom. So the derivative of the bottom is 2, 1 minus x squared goes to the power of 1. Then you have to take the derivative of the inside function, which is minus 2x, all over 1 minus x squared. You square it again, so you get a power of 4 here. And we do have to clean this up, unfortunately. So do you see that there's a 1 minus x squared here and a 1 minus x squared here? Still with me?
Yep.
Okay. So we got to do a lot of this in one step or it gets really messy. So if we factor 1 out from each of those, it cancels with this down here. It leaves 1 minus x squared times 2 minus 2x times 2 times minus 2x all over 1 minus x squared to the power of 3. Okay, so now in the numerator, you get 2 minus 2x squared, and then this becomes 8x squared over here, but it's plus. And that's all over 1 minus x squared cubed.
Mm-hmm.
So you end up getting 2 plus 6x squared on the top over 1 minus x squared cubed. So you see that the numerator equal to 0. It actually never equals 0, because when you start moving things around, you get 6x squared equals minus 2, x squared equals minus 2 over 6. So you can't take the square root of a positive or a negative, or you can't take the square root of a negative. So there's no inflection point. but because there's no critical point, but you still have to test the second derivative at those regions we talked about with -1 and 1 down there. But it looks like they're always positive because the numerator is always positive.
All right.
Wait, that's not true. That's not true. Okay, the bottom could be positive or negative now.
Oh
So
yeah.
we actually do need to test some points here. So let's say we check 10. 1 minus 10 squared is like a negative number. Cubed is a negative number. This is positive up top. So this becomes a negative. You test 0, you get 2 over 1. That's positive. Negative 10 here. It's the same situation as over here. So is your negative.
Okay.
But these are not critical points. So they're not inflection points. They're just places where the domain is undefined.
All right.
So up and down, we got those regions as well. All right.
Do you think we should do another one of these?
No, I don't recommend that, but it's
Okay.
because you said you want to do some related rates again.
Oh yeah.
There's a lot there. So just where do you want to go from here?
We can do the related rates.
Okay. All right. Do you remember which one you got on your exam?
Which problem?
Or like type? Was it the ladder problem? Was it a pond?
I know which one it was, but maybe it'll recognize. I did end up getting it right, but it felt wrong when I was doing it, but I was doing it right.
Okay.
Ooh, which one is it? That's gonna be annoying.
Well, we can just start here.
Yeah, let's just do one. I'll find it. It's in one of these. Oh yeah, hey, I have it right here. Oh wait, nope, not that one. This one. It was a triangle one. A right triangle one. It it's like one person travels south at 10 miles per hour and the other one travels east at 16.
So not anything like these. I mean, it's kind of like them, but
we'll probably, yeah, I want to do this one, but let's do the first one of
sure.
That one, and then we'll do this one.
All right, let me get that up here.
Actually, we don't even have to do this one because I have how to do it right here.
Great.
I couldn't believe I got it right, to be honest.
Well, you're in the middle of this calculus class. You definitely know enough to be able to do all these problems. So should we do 2? Should we?
Which one? Yeah, which one do you recommend?
I mean, like what I'm. Sure, we can do 2.
Okay.
Yeah, they're.
Are there no good ones on there?
I mean, they're all the same to me, frankly. But like, if I'm trying to decide which one would be helpful to you, it would be helpful to know which one your instructor gave you. But they didn't give you any like this. Well, I guess they gave you one like the 5. two people start from the same point.
All right. Yep.
Okay, 20-foot long ladder rests against a wall. Okay, so that's 20. The bottom of the ladder slides toward the wall. Okay, so that's going that way. That's weird. Okay, but that's right. How fast is the top ladder moving up? We're trying to find y prime. And when the bottom of the ladder is 6 feet from the wall. So I tend to prefer to use x squared plus y squared, even though you might use like a and b. I'm gonna use the length of the ladder here squared. So you take a derivative, and because it's related rates, there's an x prime. And when you take the derivative of y, there's a y prime and 2l prime. Okay, so this is very important. L prime equals 0 because the ladder is not changing size. It's fixed. So that means all of this is 0.
All right.
So now we need to, the thing we're trying to solve for is y prime. So we've got 2x x prime plus 2y y prime equals 0. So y prime equals minus 2x x prime over 2y. The 2's cancel and you have minus x prime over y. So you start substituting in, and you may or may not have certain values. So you don't have x, which, well, you do, I guess you do. It's minus 6. Okay, x prime is 1. Y we don't have, we have to calculate. So you calculate because, like, okay, here's a triangle. We got 20, we got 6, we got to find this other side here. Trying to decide if it's something nice. It's not, though. So it's the square root of 400 minus 36, whatever that is. I don't think that's a number. So that goes down there.
Right.
I'm gonna just pause for 30 seconds here.
Okay.
All right, I'm back.
Okay.
It's a little bothersome that this didn't work out nice, but maybe the instructor didn't.
The one on the test didn't work out nice either. It was ugly.
Oh, okay.
But the numbers were ugly, at least.
All right. So that's a straightforward one. I mean, that's now you know how to do that. You know, where do you want to go next on
I want to
this?
do the let me say mean value theorem. I think I've seen some good ones. Maybe. Possibly.
I'm sorry, say that one more time. What's the
Mean value theorem. I
mean
remember.
value theorem? Yeah. There's a problem here.
Okay, I remember it being easy when I was doing it.
Yeah, there's some like definitions. There's like, then there's actually like using it.
All right.
So I'm saying ooh. I'm looking at 37, trying to decide how to help with this. So can I pull up a different problem for mean value theorem?
Yeah, that's fine.
Okay. There's a online resource that I really like. All right, so this is sort of your classic mean value theorem problem that I'm about to snip in. And they give you a function and they want to know which numbers C satisfy the conclusion of the mean value theorem. So you gotta like know, well, what is the mean value theorem? The mean value theorem is that the derivative at a point equals the average rate of change. So the average rate of change, if you have A and B, is f of B minus f of A over B minus A.
Right.
So you have to evaluate the function at both endpoints. So it's like f of 2 minus f of -1 over 2 minus -1. So we gotta evaluate, this function here at 2. So f of 2 is 2 cubed plus 2 times 2 squared minus 2. And that ends up being minus 2. F of -1 is -1 cubed plus 2 times -1 squared minus 2. So that's -1 plus 2 minus 2. So that's also -1. Wait a second here. This first number is not right. It's 8 plus 8 is 14. Minus 2. Okay. So the this isn't right either. Is it?
I think, yeah, that's right.
Okay.
It's -1.
Is it? It's -1 plus 2.
Yeah.
Oh, I put this is minus. This is plus 1.
Is it?
Yeah, I
right,
totally messed this up. I totally messed
Yeah.
this up. Okay. So now your average rate of change, right, this up here, your A rock is 14 minus 2 over 2 minus a -1. So that ends up being 12 over 3, which is 4. Okay, so now you got to take your derivative of the original function. So the original function is up here, x cubed plus 2x squared minus x. So the derivative of that is 3x squared plus 4x minus 1, and that equals 4. And so you solve this, you solve for x.
Okay.
So the way you do that is you subtract 5 from both sides, or 4 from both sides, and then you FOIL or factor. So you get like does this one even work? Oh, this one requires the quadratic formula. Oops. So the quadratic formula gives you 2 numbers. I'll just shortcut it here. It's square root of 76 over 6, and then -4 minus square root of 76 over 6. And the problem is that only one of these is in the interval, because our interval has to be from -1 to 2. So the only one that works is this one.
What's the other one? There's mean value theorem and
there's Rolle's theorem.
Right. Yeah. Can we do one of those?
Yeah. All right, so let me look for one of those. See if it's on here.
I thought, is it? Okay. Is Rolle's theorem when you equal the, you take the derivative of the original function, equal it to the average rate of change you get?
It's a little bit different. Rolle's theorem is like this. You get a point, and then you get another point, and there's at least one place in between them where they have the same slope.
Right.
Okay. Whereas more generic, like more as what we just did here. So Rolle's theorem is slope equal to 0. Mean value theorem is a generic slope. So like this has a slope like this. And if the function does this, there's a place somewhere where it also has the same slope.
Okay. Right, that looks familiar.
But I mean, I guess it's fair to ask you to use like Rolle's theorem or the mean value theorem. So you got to know what it is. I'm trying to find a Rolle's theorem example. Let's see if I can find one here. Yeah, so here's one that we can do.
All right.
The Rolle's theorem. So they give you a function. That's got to be, that's for sure got to happen here. So they give you a function like this, and you evaluate the two endpoints just like we did in the mean value theorem. So 1 squared minus 5 times 1 plus 4. Okay, that's 1 minus 5 plus 4. That's 0. And then f of 4 is 4 squared minus 5 times 4 plus 4. 16 minus 20 plus 4 is also 0. So see how these endpoints are the same?
Yeah.
Okay. So
right.
you actually, if you do the mean value theorem, f prime of c, you're just doing 0 minus 0 over 4 minus 1, which is still 0.
Because those have to be equal in order for you to do what you're about to do.
Yes.
Right. Okay. I remember.
Yes. So then you take a derivative. So your derivative is 2x minus 5, and you set that equal to 0. And so x equals 5 halves, or 2.5, and you make sure that it's in the window.
All right. There's not one of these where you, can you scroll back up to the mean value theorem problem?
Sure.
What was the average rate of change we got?
It was 14 minus 2 over, yeah, it was 4.
And then scroll down more. Right, okay, all right. You equal the derivative to the average rate of change. You said.
Yeah, so the next one, are you talking about the Rolle's theorem? The Rolle's theorem or the previous one?
Do what?
Which one do you want me to scroll to? I'm sorry.
The mean value theorem one.
Yeah, so that's
you set the derivative equal to the average rate of change.
That's right. And then in Rolle's theorem, you set the derivative equal to 0 because the average rate of change is 0.
Right. Okay. Or can it be a different number?
No, Rolle's theorem has to be has to be 0.
And if it's not, then you're just doing mean value theorem.
Yes.
Okay, that makes sense. All right. All right, since I got an appointment for tomorrow, we can that's the last day for a test.
All right. Yeah, great.
I'll do some optimization problems.
Sounds good. I hope this is helping you, and thanks so much for scheduling. I'll see you tomorrow. Have a great night.
See ya.
Bye now.